Hello, and welcome to the team presentation by Team Sebastian on the topic of program design. Here are the team members: Diana Alberto, Justin Bramell, myself, Abhimanyu Dakwale, and Dennis Saiz Rodriguez. Programming standards. Standards are quantifiably the lowest level of mandatory requirements. However, that does not mean that individuals cannot increase the lowest level. This can be achieved by ensuring the following. Personal standards, like ensuring that the code you write is clean and well documented. Clean code refers to robust code. Code is robust if it is well designed, soundly tested, and consistent across the board. Documentation also plays an important role in ensuring that we meet all the standards mentioned here. Group standards, such as ensuring the integration of the different modules to form the completed project. For example, the test cases designed by the testing team should help the design team improve their work while also pointing out the mistakes. Project standards. Does the project deliver on its promises? Is it well tested or is it prone to bugs? Does it have any side effects? Many organizations such as MISRA, JSF AV, and CERT have developed coding standards concerned with safety. These can also be referred to or additionally implemented to help stay on track. Guidelines such as JSF AV C++, MISRA C, and CERT Java, to name a few, could be beneficial to us. Header design. Headers help implement object-oriented design principles. Headers are good examples of abstraction and modularity implementation. A header file should be concise in its coding, yet descriptive in its documentation. This helps a person read a header file without context and yet derive the functionality that this file would implement. Due to a header file being used in multiple different programs at the same time, the replication of the same code is prevented. By being a module of a greater program, it also helps us to catch errors easier. Since we know what methods and functions this file is calling, we are able to narrow our search down.
You should follow these standards regardless of the purpose of your code. A program should be toolable. A toolable program has the ability to be able to be used by other programs. It can be easily parsed and manipulated by other applications. An example, if you try to open a media file, let's say an MKV extension in a new computer, it is likely that you get an error message. For instance, in Windows or Linux, you'll get an error message saying that the file format isn't supported. This will happen even if you have media player software. The solution will be to install a codec, a computer program for encoding or decoding digital data. Your application will be able to use this codec software as a tool to decode media files. After you've installed this program, your media player application will be able to play many previously unsupported files format. Your applications, for instance Windows Media Player or Movie Player, will be able to use this codec software as a tool to decode the media files. Your program should also be portable. What is a portable program? A portable program has the ability to run successfully across different compilers, operating systems, and hardware platforms with little or no change to the source code. In general, software written in Java has this ability. Java was created using the write once, run everywhere philosophy, and it should produce identical results regardless of the CPU, operating system, or Java compiler. Is Java the only program to produce portable program? Well, languages such as C or C++ provide portability. However, they leave undefined details such as the size and endianism, the behavior of floating point math, the value of uninitialized variables, and the behavior when free memory is accessed. Why don't we use Java everywhere? Well, the problem is that features that make Java so portable have a downside. Java assumes a 32-bit machine with 8-bit bytes and IEEE 754 floating point math. Machines that don't fit this model can run Java efficiently. An example of portability is in previous courses at USF, we've been asked to write small programs using C or C++, but before we submit it, we need to make sure they run in the C4 lab machines. If you code using Windows machines like I do, chances are that you'll receive several error messages and you try to compile and run your code unsuccessfully, especially if you're working with data path files. Your program should also be reusable. Reusability is the ability of a piece of code or software to be used to build a new software or complement an existing one. This is the as the don't repeat yourself. Very few information systems are designed and written entirely from scratch. Applications are built upon frameworks and routines that programmers have written in the past. It is important to know that code reusability is not about copying and pasting code. Instead, you should try to make your program accessible and suitable for future. Some examples of reusable programs or code can be seen in web frameworks like Django, Flash, Ruby on Rails, or the .NET framework. You can also see it in libraries, exceptions, string, iterators, or string, regular expressions, and thread. Your program should also be testable. Software testability is the degree to which a program or module supports testing in a given test context. How can you make your code testable? Well, you should break your code into individual subsystems and modules. For example, you can separate distinct areas of functionalities like data retrieval, data processing, data display, or event handling. This makes it possible for components to be easily replaced with mock objects during testing. An example would be this function. Uh, it gets the time of the day, it gets the time from the computer, and then it returns if it's 9 evening, morning, or the afternoon. Now there is a problem with this first line in the code. The daytime now is a hidden input. You don't control it. It is almost impossible to test this function without changing the time in the computer. A solution could be to replace this uh, the way we get the time and pass as pass an object as a parameter. That way you can access the function, pass a parameter that can you can specify the time at any given moment. Your program should also be reliable. Reliability refers to the consistency of a program in its execution. It is the probability that a system will operate without fault or failure under given environmental conditions for a specified period of time. System failures can affect large number of people, can cost a lot of money, and can completely shut down basic services like communications, transportation, and medicine. It is important that you know that if a program has never failed, it doesn't mean it's 100% reliable. Errors can occur without a warning. For instance, on February 25, 1991, during the Gulf War, an American Patriot missile failed to track and intercept an incoming Iraq missile, killing 28 soldiers and injuring over 100 other people. This was caused by an inaccurate calculation of the time. Turns out Time was calculated by multiplying by 10 and thus getting the time in seconds. Since the machine had a 24-bit architecture, there was a small chopping error when multiplied by a large number. The computer had been around 100 hours, resulting in a significant error of 0.34 seconds. This kind of missile travels at around 3,750 miles per hour. Ironically, time calculation had been improved in some part of the code, but not all. Your program should also be enhanceable. An enhanceable code is enhanceable if it allows changes to increase performance or adapt to future changes. Software development does not stop when a system is delivered, but continues throughout the lifetime of the system. Parts of the software may have to be modified to correct errors, adapt to changes, or improve performance. According to the textbook, about two-thirds of the software cost is associated with evolution costs, meaning the companies spend more on maintaining and enhancing existing systems than on new software development. How can you make your program enhanceable? Well, you can make it more understandable. You have to ask yourself how difficult it is to understand your code, how complex are the structures that you use, do variables have meaningful names, documentation, is your documentation complete, consistent, and current? You have to ask yourself if the programming language that you use is still in use today, and how much support exists in the community. You have to also see the structure of your program. Is your program well structured? Is dependability contained in a separate modules? An example of enhanceable uh, software can be seen every day. Companies are constantly trying to enhance their product, keeping up with current trends and solve security and performance issues. For instance, Chrome lets you install extensions, making the browser more suitable for everyone. You can make it your own and make it a very powerful machine or tool. Your program should also be fixable. Fixable is the ability to be fixed within a program, preferably quickly and easily. Developing software is very expensive. If a program can be fixed, the company will face big losses from either throwing away the software or losing customers or resources as a result of errors. An example would be the iOS updates or the Windows. These programs, these softwares can be updated and fixed. If we had to replace the whole system, we probably wouldn't have computers today. Your program should also be consistent. Consistent refers to the reliability of a program to perform correctly. It is also referred to the readability of your code, standards, and compliance with architecture. Consistency can mean many different things, ranging from coding style to choice of libraries and architecture designs. Any large code base with multiple teams members should look as if only one programmer wrote it. For instance, you can either choose style 1 or style 2. You shouldn't mix these two since your program won't be consistent and it will be harder for another programmer to read your code.
Control structures. A control structure is a block of programming that analyzes variables and chooses a direction in which the program will proceed in based on the given parameters. The term flow of control details the direction the program takes, that is, which way program control flows. This block of code is helpful in making decisions and following different paths as consequences of those decisions. These structures also help move the control of the program using statements like break, continue, go to, etc. Control structures help the program be more robust and generally lead to cleaner code. They also improve the reusability of the code as the statements need only a different set of preconditions to function differently. There are two main types of control structures: iteration and selection. Iteration: a control structure where a loop is run that allows a part of the program to be executed multiple times. There are three types of iterations: for loop, while loop, and a do while loop. Selection: a control structure that implements only one case of code if the conditions are met. This implies that at any given time, only one output would be received from this type of control structure. If then else. Algorithms. The simplest definition of an algorithm is that it is a method, a set of steps, which when implemented leads to the task being accomplished. It could be as simple as brushing your teeth or as complex as the P versus NP problem. Any activity that we perform daily can be broken down as being the result of implementation of an algorithm. The importance of an algorithm stems from the order that it provides to programmers to write the code that works. An algorithm provides the basic framework for the code, which can then be extended upon depending on the user's will. The two main goals of any algorithm are correctness and efficiency. Correctness: the correct answer to a particular problem. Example: the best answer to an optimization problem. Efficiency: an algorithm needs to be efficient. This efficiency comes in varied forms, with the most common being a greater understanding of the functionality leading to easier translation. A good algorithm allows for flexibility while maintaining its simplicity. Data structures. Data structures help us organize and process our data. There are many different data structures that we can choose from. The different types of data structures are built-in data structures, integer, float, character, pointer, or user-defined data structures like arrays, lists, and files. Lists contain within themselves subsections of data structures. They can be linear lists like stacks and queues, and nonlinear lists like trees and graph. Here is a flowchart which accurately describes the different data structures that we just spoke about. From so many data structures to choose from, how do we decide which data structure to pick? The choice should be dependent on one main concern and one sub-concern. The one which provides maximum efficiency should be used. The data structure which is appropriate for a particular problem will be the most efficient for that particular problem. Second, the level of comfort you as a programmer have working with that data structure. It is important to note that while the first concern usually takes precedence, the second concern is equally viable. No knowledge of a particular data structure implies no program with that data structure from that programmer. General guidelines. Pseudocode is an extremely important aspect of the software development process. If an idea is conceived with the help of an algorithm, it is given life with pseudocode. Pseudocode helps get the requirements of a project from the design team across to the programmers. There are different stages during the development process, and pseudocode plays an important role in each of them. We have initial pseudocode, which is simple, verbose. It explains everything. We also will have a final executable pseudocode. This pseudocode is usually one step short of actual code. This is an example of a simple pseudocode to calculate the sum and average for 10 numbers. This is an example of an executable pseudocode which is implementing the quicksort functionality. General guidelines. We need to break the code into smaller, focused units. Ensure that each method, function, and logical block of code does its job well. Revise and rewrite, not patch. No one's first draft is perfect. Therefore, this is an important practice that one must be willing to partake in to ensure quality of work instead of patching. Revise. It implies that your code is working towards the goals, just maybe not efficiently. Maybe there are a few errors, but your overall program looks to be heading in the right direction. Rewrite. Rewrite implies that your code needs to be overhauled almost completely. This could be due to the wrong information, lack of foresight, problems with data structures, and so on. This needs immediate attention. The last thing that we shouldn't forget is to comment and document. Code reuse. Code reuse is an application of the object-oriented design principles along with being a key derived property of robust code. The key to writing reusable code is to write focused, composable components with a high cohesion and loose coupling. High cohesion implies that the class or method does its job well. Loose coupling reduces the risk that a change made within one part of the program will create unanticipated changes within other parts. Remember, don't over-design. Keep the design focused on the task at hand. If the code becomes too complex to be reused, then it simply would not be reused. The code that you write should be robust. If a program is robust, it is possible to easily assimilate the code into a different program's implementation. There are some factors which must be considered when you're thinking about reusing code. Ensure that the code is correct and provides the defined functionality without side effects. Side effects could affect your code and the third party's code. Ensure that the code has been regularly maintained and periodically updated. Remember, code could contain outdated components. Ensure that there is proper documentation for the code that you're trying to use. The programmer may or may not be available for comment if you run into a program while working on the third-party code. Therefore, it is essential to ensure that there is proper documentation for the code.
So now we're going to talk about documentation. In program design, documenting your code properly is a very important concept. So what is documentation? Documentation is just a set of written descriptions that explains to a reader what a program does and how it does it. Its purpose is to help people who didn't write the code to understand the code or the overall software product. And there are two main types of documentation, internal and external. Internal is descriptive material written within the code. External covers everything else. So like I said, having adequate documentation in your program is extremely important for a number of reasons. One is when you work in a team of software developers, you each will write separate components that other people will need to be able to use and integrate into an overall software system. And if they don't know how the components work and how they what their behavior is, then they can't do that. It also helps facilitate code reuse, since to be able to reuse a piece of code, again, you need to know its behavior and how it operates. It also is useful for non-programmers and non-technical people to understand how your program works. And oftentimes, you'll be working with legacy code and old code bases that were written by someone who is no longer around, who no longer works for the company you're at, for example. And so if they didn't document their code properly, then it becomes very difficult to use and to maintain. So internal documentation. Internal documentation is directed at those who will read the source code of your program. It should contain summary information about components, such as the data structures, algorithms, and the control flow that the components use. It's usually placed at the beginning of each component in what's called a header comment block. A header comment block should contain things like what a component is called, who wrote the component, where the component fits into the system, when the component was written and revised, why the component exists, and how it uses its data structures, algorithms, and control. It can also contain more detailed information, such as input and output, aids to testing, future revisions or extensions, and names of major variables and data structures. So a second type of internal documentation is comments. And comments are meant to guide a reader through step-by-step execution of the code. And they're meant to be a way to clarify complex portions of the code or let the reader know what a variable does, for example. But it's important to not have too many comments in your code because that can often make it less readable and less understandable. So you want to minimize the amount of comments in your code by using descriptive labels, variable names, and data names. And also comments should add new information and accurately reflect code behavior. And here are two examples. On the left, we have a header comment block, and on the right, we have some examples of comments. And again, meaningful variable names and statement labels. It's very important to choose names for variables and statements that reflect their use and their meaning. So here we have an example, z equals a times b plus 0.5 times a times b minus 40. And when you look at this line of code by itself, it's really impossible to abstract any meaningful information from that line. The second example, where we're using descriptive names and variables, you can read that line and determine that you're just simply calculating a weekly wage. So again, using these meaningful names and variables helps your code describe itself to a certain degree, and in this way you can minimize the number of comments that you need. Also, you want to format your code to help enhance understanding. So here we have two quick examples on the left here. There's no indentation and there's no formatting in the control logic. So it's really difficult to look at that and kind of understand the purpose of that control logic. Whereas on the right side, you have proper indentation and proper grouping of the control logic, and it's much easier to look at that and read it and understand it. So part of good documentation is, again, choosing descriptive names for your variables and formatting your code properly. And then finally, documenting data. So documenting data is very important because one of the most difficult things for readers to understand when they're reading your program is how your program is interacting and manipulating data. Your program can have many different data dependencies, files, databases. You can also use a variety of complex data structures. So you want to use a data map, which is meant to help the reader interpret what the code is doing with data. It should show when and how a portion of the program interacts with data. It should correspond with the data dictionary and external documentation. And now we move on to custom data types. So part of program design is sitting down with your team or whoever you're designing the program with and kind of brainstorming about what, if any, custom data types you'll need. So some examples of custom data types you can use are classes, structs, and type definitions. Here we just have a quick example of a class as a custom data type. So in this instance, person created a custom data type of bicycle. And I'm not going to go into too much detail about what a class is because we already covered that. But here on the left, you see the bicycle class. It's got its data members, its methods, destructor or constructor rather. And then on the right is just a quick example of how to initialize that. And now we have what's called a struct. So a struct is a data type for when you need to group multiple variables of different types together. And again, just a quick example, you can create a struct student that groups together a string name and an integer ID. And then here's a couple examples of how to initialize a struct. And then finally, we have a type define. So a type define is a way of renaming a built-in data type, such as integer or character. It can help to document your code by making it more descriptive, and it can help the readability of your code. Because if you, for example, if you have a lot of elements in your code that are represented by an integer, different elements, then you can type define an integer to those different elements in order to make your code more descriptive. For example, you can type define an int to int16 if you need a 16-bit integer, or you can type define a float to float 32 if you need a 32-bit float number. And you can also rename custom data types such as a struct.
Memory management is a form of resource management applied to the computer memory. It is also the process of allocating new objects and removing those unused ones to make space for the new allocations. It is usually divided into three areas: hardware, OS, and application. To the right, we have an example of a high-level representation of the memory in the computer. We have the program data, where the program codes and static variables are, the heap, where objects created via new leaf, we have some free space, and the stack, where the function's parameters, local variables, and returns our values are. We also have a low-level memory management. For example, C provides four basic functions for memory management: malloc and calloc to allocate memory, realloc to expand the previously allocated memory, and free to deallocate the memory. We also have an example of a code that is using some of those functions. C++ provides a higher level of memory management through the constructor and destructor and the new and delete functions. We can also see how the same example that we saw in the previous slide had more line of codes. This example now in C++ is more compact and is more efficient because the string class takes care of all the memory management, leaving the programmer not to worry about it. Some of the problems that we have for using the memory management in an incorrect way are freeing or overwriting data that is still in use. This leads to memory corrosion, which typically results in the application crashing or corrupted user data. We also have an issue when not freeing the data that is no longer in use. Memory leaks is caused by this, which in time causes the application to increase the amount of memory, and it also brings as a result a poor memory performance or the application being terminated. Therefore, good practices prevent memory-related problems. We move now to another topic that was mentioned in the documentation previously, and is code formatting, which is the way of arranging a program to enhance readability by using indentation, alignments, and white spaces. Some of the commonly used formatting conventions include indentation and white spaces. Indentation refers to one or more spaces left at the beginning of the statements. It is used to highlight nested blocks required if a statement is large enough to fit in a single line, and should be consistent at the beginning and at the end of the braces. On the other hand, white spaces improve readability by minimizing the compactness of the code. And some of the conventions include there should be a space after placing a comma between two functions' arguments. There should not be a space between a function name and a parenthesis, and there should be spaces to align operators vertically to emphasize the program structures and semantics. Internal comments are another way to bring structure to the code, and is useful in proper understanding of the code segments used in a program. Some of the convention includes the file header comments and the trailing comments. Those are very important to types. The first one provides information related to a file, such as the date of the creation, the name of the author, and a brief description of the program. The trailing comments provide explanation of a single line of code. They clarify complex codes or variable names, and they are placed throughout the body of the program. Sometimes double slash is used. And for the conventions, comments should not be used to include information that is clearly understandable from the software. Comments should be used with important segments of code that are difficult to understand, and comments should be separated from the code to enhance readability. And this picture is kind of funny, but at the same time it brings truth, because if you see the programmer is just saying, I have no idea what this function does, it seems to be important, please don't touch it, and then he's saying that good comments are essential to deliver high quality. So this is a good example of what we shouldn't do in code. Code fragments are small blocks of code that occur regularly in programs, so they can be collected for reuse. They are also called snippets. They are usually used for simple sections of code such as copyright notices, function prototypes, common control structures, or standard library imports. And primarily, they are used when abstractions such as methods are not available or not desired. In this example, if the new property value is changed, then all the instances of the class will be changed. At the same time, if a string is changed to an int, the set methods or the methods will change too. We have talked about how to format our code, but why is it important to format the output? Formatting the program output is an essential part of any serious application. For example, C provides standard functions such as printf to format the output. And some of the parameters that this function accepts or specifiers are D for int, F for floating, S for string, and C for character, and so on. It is also important to have a grateful exit when deallocated temporary memory. Grateful exits is when a program detects a serious error condition and exits gratefully in a controlled manner. Often the program prints a descriptive error message to a terminal or save it as a log as a part of the grateful exit. The code associated with the grateful exit may also take additional steps, such as closing the files to ensure the program leaves data in a consistent, recoverable state. All the software or the programs, they require input, any kind of input, and it might be from the user, from another application, or from a malicious user. As a result, input validation is very important. An input validation refers to the correct testing on any input that is supplied by something else. Problems resulting from incorrect input validation include buffer overflows, injection attacks, denial of service attacks, memory leakage, information disclosure, and compromised systems. We can see an example of a Java code that is trying to validate if the seed code provided by the user is good or is wrong. But be aware, having many or multiple validation is also dangerous. As a result, avoiding multiple validation is crucial in designing efficient applications. This code is also trying to do validations in the input getting taken by the user, and it has validations for the emails, for the name, for the age. Look how many lines or how many if statements it has. On the other hand, we have another version of the same code or the same problem where abstraction is used by creating classes and creating methods that are only doing a specific function. So the new version is more compact, readable, and testable, and of course more efficient. Handling errors refers to the anticipation, detection, and resolution of programming applications. Main type of errors include logical errors, syntax errors, semantic errors, compile time errors, and runtime errors. The logical errors, the syntax, and the semantics usually put pressure on the programmer. It's like how we as programmers, how efficient we can be on doing our code. And C has also dedicated error functions such as p-error or str error. But there is also tools that help dealing with the errors. For example, Chrome dev tools provide the developers with a way to fix web pages through init sessions and debug errors in JavaScript. Also, the Adobe Code Fusion provides tags and functions for developers to use to customize error handling. As a result, it helps making the development process easier.
All right. So now back to documentation for a second. So we talked about internal documentation earlier, but there's also external documentation. External documentation is intended for those who will never read the source code. So, for example, designers, clients, managers, non-programmers, non-technical people, and even end users. And external documentation should give a broader explanation than internal documentation. So if you think of a header comment block as a summary of a component, then an external documentation of that component would be like a full report, a lot more detail and information. It should answer who, what, why, when, where, and how, but from a system perspective. So it should explain how components fit together and how they share data, interact in the overall system. And it should also have diagrams alongside the narrations to describe each component. So the diagrams should describe how data is shared and used by one or more components and how information is passed from one component to another. Two kind of simple examples of external documentation would be a library documentation and end user documentation. So there are three main parts that you should have in your external component documentation: describing the problem, describing the algorithms, and describing the data. When describing the problem, you want to explain what problem is being addressed by the component, so what the component's purpose is. You also want to have a general discussion of setting, explaining when the component is invoked and why it's needed. So you want to kind of put the component in the context of the overall system. Then you want to describe the algorithms. So for each component, you want to describe each algorithm that's used. You want to describe any formulas or boundary special conditions used in the algorithm, and also any special cases. And then finally, describing the data. You want to provide a view of the data flow at a component level with data flow diagrams and data dictionary references. And you can also have, if you're using classes, an overview of classes and objects relationships. And here are two examples of that. On the left, we have a class hierarchy diagram. And then on the right, we have kind of a system component view of a student login, registration, and billing system. So now we're going to talk a little bit about some processes, programming processes, and problem-solving processes. So at the heart of programming is solving problems. You're given a complex problem, and you have to craft a solution to that problem. So it can be helpful to look at some general problem-solving processes that you can apply to creating software. So in 1957, a mathematician, Polya, wrote a classic book on problem solving in which he described 4 distinct stages to solving a problem. You need to understand the problem, devise a plan, carry out the plan, and then look back. When understanding the problem, you want to understand the conditions under which the problem must be solved. So you want to analyze each element of the problem and ask these questions. You want to ask what is known, what is not known, what is possible to know, and what is impossible to know. And you should try to address both data and relationships. It can also be helpful to draw pictures to understand a problem. You can draw flowcharts and diagrams showing how data structures are changing, for example. You can also use drawings to help decompose a complex problem into subproblems, which is a very important concept in computer science. Take a complex problem, divide it into subproblems that are easier to solve, and try to solve those. And you can also divide those subproblems into smaller problems. So it's a recursive process. Then you need to devise a plan after you have understood the problem. Polya described 3 main techniques for finding the right plan. You can identify a related problem and ask, are there any data algorithms, libraries, or methods we can use to attack the problem? You can restate the problem, the key definitions, see if you can generalize or simplify the problem to gain new insight. And again, you can decompose the problem into its essential elements. Then you need to carry out the plan. You need to verify, you need to implement the plan step by step, and at each step you need to verify the solution. And once you're done, you look back, examine the solution, ask, is it reusable? Can it be used to solve a different problem? And then we have extreme programming. So whereas the method I just described is more of a general problem-solving method, this method is more of a software development methodology. It's a programming process with the goal of increasing software quality and responsiveness to changing customer requirements. There are 2 main participants in this process, the programmers and the customers. And where this process kind of differs from others is the customers are working very, very closely with the programmer throughout the entire software development cycle, constantly providing input and new requirements, updating their requirements, and so they have a constant influence in the development of the software. So again, it's based on the agile methodology, which emphasizes frequent releases and short development cycles. And this is intended to improve productivity and introduce checkpoints in which new customer requirements can be introduced. So basically, you might have, for example, a 2-week development process, and at the beginning, or cycle rather, at the beginning of that cycle, the customer will meet with the programmers. They will give their features that they want to be implemented, and they will prioritize those features. Then the programmers will code the features, test them, and then release a finalized product at the end of that cycle, at which point the customer again will meet and review that cycle, or review that product or that code release, and be able to update the requirements or scrap something entirely. Maybe they decide they don't want a feature anymore, they want the feature to be different. The programmers will then take those updated requirements and start a new cycle. So it uses paired programming, unit testing, and again, prioritizing features based on customer priorities. And it takes its name from taking beneficial practices to the extreme. For example, paired programming is code review in the extreme. Code review is just writing a section of code and then once you're finished, handing it to someone else so they can review it and give you feedback. Whereas paired programming is that concept taken to the extreme, because someone is reviewing your code, but real time as you're writing it right behind you. and interaction with customer to get requirements. Again, that's viewed as a beneficial practice in the industry. You need to get requirements, to deliver what the customer wants. But in this process, the customer is constantly updating the requirements during each cycle. Then finally, we have pair programming. Pair programming is when two programmers use a single keyboard, display, and mouse. One acts as the pilot who controls the computer, writes the code. One acts as the navigator who reviews drivers, code, and provides feedback. And there have been multiple studies arguing for and against paired programming, and there are pros and cons. Some of the pros are if you pair up an experienced programmer with, let's say 10 years of experience with a novice programmer just fresh out of college, there's going to be a lot of opportunity for that novice to learn both how an experienced programmer thinks and also how they write their code. And the pros are another pro is you can catch errors early because you have two sets of eyes, and also it builds team synergy. Some of the cons are it can actually inhibit problem solving because you're being forced to interact with someone, and it can disrupt your focus. Also, good problem solvers might be overshadowed by people who are better at kind of talking and communicating their ideas, even though they might lack analytical skills necessary for difficult design and coding tasks. So the person who has stronger analytical skills but is more introverted might not do as well and be less productive in this environment. And finally, good problem solvers need time to think alone, to devise their plans, and to analyze their potential solutions. And paired programming really doesn't give you the opportunity to just be by yourself and think. Okay, so that concludes our presentation. Thanks for watching.